We've talked about a number of ways to look at how certain forces cause changes in objects' motion. Earlier in the year, we discussed F equals ma, and we talked about how if we knew what the net force on an object was, we could determine how a certain mass accelerated. This could also be done rotationally using torque and inertia and angular acceleration. We also talked about, more recently, ideas of energy conservation. We wrote equations, that might look something like this, how potential energy, maybe of a ball, released from up high, and how then later in its fall it still has some potential, but it also has some kinetic. And that was another way of examining how, in this case, the force of gravity affects an object's motion. We could involve work and so forth in that as well. Well, a third method is to look at momentum and impulse. And we're going to begin by defining those terms, but then later in this unit, the real important part is going to be when we look at interactions between objects, such as collisions or explosions. You might remember this from last year, how momentum describes an object's resistance to stopping or changing its motion. Sometimes it's referred to as moving inertia. And so linear momentum is defined, or it's given the symbol of a little p. It actually is a vector quantity, so we really should put some vector notation above the p and the v. Again, it describes an object's motion, but it also takes into account how big the object is. So the idea that if someone throws a basketball towards you or throws a bowling ball with the same speed towards you, it's going to be a whole lot harder to stop the bowling ball than the basketball. And that has to do with this idea of momentum. The units for momentum are pretty straightforward, no special name or anything. Mass is measured in kilograms, and velocity in meters per second, and so your units are kilogram meters per second. But just describing an object's motion and even including that mass isn't enough to really explain how it changes that motion. And so impulse is the way that we describe the change to an object's motion via a change to its momentum. Impulse is defined as a force times the time during which that force is being applied. And again, this is a vector quantity, so the impulse has a direction and the force has a direction. And if you're just working with constant forces, this is about all we would have done in the first year course. The impulse has units of a Newton times a second. If you go through and substitute in what a Newton is, a kilogram meter per second squared, you get the same units for momentum. So it makes sense that we can sort of equate impulse with the change in something's momentum. But if that's all you do, there's really no point in working with impulse and momentum, because you could do the same thing with F equals ma. It really doesn't tell us anything much different, since an acceleration is a change in velocity over time. Then all we're doing is we're saying if we take the net force and we multiply it by the time, we get the mass times the change in velocity, or impulse equals change in momentum. So why do we want to talk about this? Well, for one thing, sometimes we are given information about forces where the force is a function of time. And so in that case, it's useful to use an integral form of this, where you're adding up small values of force as time progresses. And so if you integrate the force function with respect to time, or if you look at the area of a force graph as a function of time, you can determine this impulse. And again, that relates to the change in something's momentum. A lot of times, though, we are just interested in average forces, and so it kind of goes back to a simple form of what impulse is. Note that these functions that I circled here, that has to be a function of time. In a previous unit on energy, we were working with forces as function of position, and that dealt with work and change in energy. This is a force as a function of time, so that's going to lead to an impulse and a change in momentum expression. This is a slide that you might want to just stop and read through a little bit. But just like we had three different ways of sort of dealing with work, we have three different ways of dealing with impulse. So if you have a function, then you'll end up integrating to find values of impulse. If you have a graph, then you're going to be looking at area. And if you're just looking for a constant value or an average value, then it drops back to the simple form of impulse equals force times time. But do always keep in mind that the direction of things do matter. These ideas of impulse and momentum are vectors, as opposed to the energy ideas, which are scalars, where the direction does not matter. All right, let's delve a little bit deeper into the exact connection between impulse and momentum. Again, the phrase is that impulse equals the change in an object's momentum. Okay, so why is that? Well, if impulse up here is the integral of force dt, and if we think about that, a force can be expressed as an object's mass, which is constant, times its acceleration. You can pull that mass out of the integral, and we're just left with this. Okay, but that has a distinct meaning to it. We talked about this earlier. The change in velocity is equal to the integral of a dt if we are looking at two specific times. So if we look at the definite integral, it does give you these specific values. And so that would just be our change of velocity, our second velocity minus our initial velocity. So we're able to say that impulse, again, which we could find by either integrating a function or taking a constant force times time or looking at the area, that is going to equal an object's change in momentum. Okay, so we've got a number of ways of looking at that. It's very similar to how we dealt with questions with work. We had what was called the work energy theorem, where if we knew the initial amount of energy, often kinetic energy, and then we added the work being done, and that might be positive or negative work depending on whether the force helped or worked against the object's motion, that determined the final value of energy. So that's what we were dealing with when our force function was written in terms of position. But if instead our force function is written in terms of time, then we would think about this a little bit differently. We would want to work more with something where time is important. Remember, energy, it was all just about initial position, final position. It didn't matter the path. But if the path matters, if the time of the motion matters, then the initial momentum plus the impulse, and again, that could be positive or negative, determines the final momentum. And so we'll approach these questions in a similar way to what we did earlier. There's a second video that has an example that's available off the website. One last comment, the way that these formulas are written on your formula sheet might look a little different than how I might write them in class or how you might write them on your homework. But these are the three formulas that are given: a definition of momentum, a demonstration that impulse is equal to the change momentum, and a definition of impulse. But notice only the integral form is used. So you've got to know that if force is constant, you're just thinking F times T. And then this one comes up just seldom. It's just kind of a rearrangement of some of these ideas that may or may not come up. We'll just kind of see what happens.